This section is titled Higher Order Polynomial Functions and Their Graphs. So first let's talk about what a polynomial is. We have this polynomial f of x is equal to a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 a sub 2, and a lot of students look at this going all the way down to plus a naught, and it looks very scary to them. This is just a polynomial, meaning we have coefficients in front of the x's, like 3 or negative 2 or a half. And we have x's with whole number exponents, and that's just what a polynomial is. So for example, f of x is equal to 2/3 x cubed plus 11x minus 17. This is a polynomial. Notice we have only one variable, x. All of the exponents are whole numbers, and all the coefficients are real numbers. So that would be an example of a polynomial. The degree of a polynomial is just going to be the highest exponent that you see. And in this case, the highest exponent would be n, or the highest exponent. The degree of the function that I gave you as an example would be 3. The leading coefficient is the coefficient of the term with the highest degree, or the degree of the polynomial. So in this case, the leading coefficient is the number in front of x to the n, or a sub n. In our example problem, our leading coefficient would be 2/3, the number in front of x cubed. Because 3 is the highest exponent, then 2/3 is the leading coefficient. We're going to be using these terms throughout this whole section and later on in the chapter as well, so we'll need to know those. Our goal of this section today is to graph polynomial functions with exponents higher than or equal to 2. If we have a degree of 2, we know that's a quadratic function, and we already graphed quadratic functions. We're now trying to mostly focus on ones that are higher than 2, but this still works with an exponent of 2. I want you to know that polynomials always make smooth graphs. No stops or starts, no sharp points. At the ends of the polynomial graphs, f of x is going to either increase to infinity or is going to decrease to negative infinity. So it'll either go up forever or down forever on the extremities of the graph. But in the middle of the graph, you may have several peaks or valleys. Or you might call them bumps. So for example, I could have a polynomial that on the extremities, let's say, goes down forever, and it does some possibly weird things: bumps, valleys, peaks, high points, and low points or valleys. And we could call these bumps. It could, let's say, start up forever and do a couple of bumps and then also go up forever. These are just two possible examples of polynomial functions, how they might look. My peaks are the high points. The valleys would be these low points. And if you put those peaks and valleys together, we can call them bumps. And I want you to know that the number of bumps will always be less than or equal to n minus 1, or the degree less 1. We'll be using this information a little bit later on. So in order to graph general polynomial functions, we need to know the function's end behavior. We said in the extremities it either increases to infinity or decreases to negative infinity. It's got to do that on the right-hand side of the graph, or it's also going to do that on the left side of the graph, as x gets very, very large or as x gets very, very small. So we need to know what happens at the ends of the graph, and that's called end behavior. Secondly, we need to determine the X-Intercepts, and there can possibly be more than one, and we also call these zeros. We also would like to find the multiplicity of the zeros, if there is any. Next, we'd like to determine the Y-intercept, there is only ever one y-intercept, so I'm not going to put the parentheses with the s on it because there will only ever be one y-intercept, although there could be several or none x-intercepts. So first we need to know the function's end behavior. So we're going to take a little bit of time to study what end behavior is and how to find end behavior. End behavior is what the function does as x gets very large and as x gets very small. To determine extreme or end behavior, what we're going to look at is the degree of the polynomial. We've already talked about using the letter n for degree. And we also need to know the leading coefficient. And we've also talked about using a sub n for the leading coefficient. So if I take the degree and the leading coefficient, and I identify whether the degree is either even or odd, and whether the leading coefficient is either positive or negative, I can tell what happens at the extremities of the graph. If my degree is odd, yet I have a positive leading coefficient, my end behavior will be going down forever to the left and up forever to the right. What happens in the middle of the graph? Well, I don't really know at this point. All I know is that I have an odd degree and a positive leading coefficient. My end behavior will go up forever to the right and down forever to the left. An example of that would be f of x equals x cubed. What's my degree here? My degree is 3, and 3 is odd. My leading coefficient is 1, which is a positive leading coefficient. So we have an odd degree and a positive leading coefficient for this example. We actually already know what this looks like from previous sections. What happens to the end behavior here? We have an up forever to the right and a down forever to the left. In this particular case, we actually know what's going on in the middle of the graph because we actually know this graph quite well, although on some of the ones that we'll be looking at later, we don't exactly know what's going on the inside of the graph, we just know the extremities. Next, we'd like to look at an odd degree with a negative leading coefficient. Well, an odd degree and a negative leading coefficient is going to go up forever to the left and down forever to the right, exactly opposite of what the odd degree and the positive leading coefficient does. What happens on the inside here? Well, I don't know. Possibly lots of things could be going on. I'm not sure what's going on in here. We'll have to find the zeros to be able to figure that out. But for now, we need to know that you go up forever to the left and down forever to the right. An example would be f of x equals negative x cubed. Notice my degree is 3, which is odd. My leading coefficient is negative 1, which we note is negative. We know how to graph this from previous sections. I know it has a cubic function as a parent function, but because the negative's out in front, it's reflected over the x-axis. And it will look something like this. Because we know this function so well, we can identify that this truly does match our end behavior. It goes up forever to the left, like we said over here, and it goes down forever to the right, which is what we said here. Notice for both odd degrees, the arrows are pointing in different directions. Well, for the even degrees, the arrows are going to be pointing in the same direction, either both going up forever or both going down forever. So an even degree with a positive leading coefficient is going to go up forever in its extremities and up forever in its extremities to the right and to the left. What happens in the middle? Possibly lots of very interesting things. I'm not quite sure, but all we really care about for the time being is that it goes up forever and up forever to the left and to the right. An example of that would be f of x equals x squared. That's a quadratic parent function. We know that one quite well. This is what the quadratic function looks like from our previous knowledge. Notice that the end behavior does match the end behavior of an even degree and positive leading coefficient. The degree is 2, which is even. The leading coefficient is 1, or positive. So this does match our even degree and positive leading coefficient. And lastly, an even degree with a negative leading coefficient is going to have end behavior going down forever to the left and down forever to the right. Again, in the middle, I'm not sure what's happening. I don't really care about that for now. I do know that it goes down forever and down forever. Let's take a look at our example. F of x equals negative x squared. Well, we know what that one looks like. We do have a degree of 2. My leading coefficient is negative 1, which is negative. My degree is 2, which is even. I know what this looks like from previous knowledge. I know it's a quadratic function, but because there's a negative in front, it's reflected. And my end behavior does match the end behavior of an even degree and a negative leading coefficient. You will have to know this chart, at least this top part right here. You'll need to know it by heart so that when you get to the problems on the test or on the homework, that you'll be able to quickly know the end behavior. So this is something that you're going to have to memorize. One way I like to remember the degrees is I kind of think of it as a dance. And if I was standing in front of you today in class, I would be using a polynomial dance to remind you what to do here. If it's an odd degree, I want your arms to go one up, one down. That looks kind of odd. If I was standing up in front of the class with one arm up and one arm down, kind of like a dance pose here, that would look a little odd that your teacher's standing up in front of the room doing this odd position here. So this is odd yet positive. And then if it was odd but negative, my arms would just be going in the other direction. Notice that this is kind of like an uphill slope. So a positive leading coefficient is kind of going uphill. So kind of like a positive slope, but the arrows are going in different directions. So again, it's odd degree, so your teacher's standing up in front of the room looking a little odd because she's got her arms pointing two different directions. And in the negative case, we have the slope going downward, kind of. I know it's not truly a slope, but it's kind of like we're going downhill eventually. I know there's some weird bumps and valleys on the inside, but on the extremities, I'm going up forever to the left and down forever to the right. That's like a downward motion. So that's a negative leading coefficient. So that's how I remember that one. For the even degrees, again, if I was standing up in front of the class and I had my arms up like this, notice that my arms are both pointing up, and that's like the left side of my body is even with the right side of my body. They're the same. They're kind of even, or they're kind of symmetrical. So that's why I think of even. Odd looks like I'm doing something funny because I've got my arms in different directions. Even's nice and even. The left side looks like the right side. And a positive coefficient makes sense because positive is going up. So a negative yet leading coefficient yet an even degree. Even degree tells me that my arms need to go in the same direction. Negative tells me that they're pointing both downward. Okay, so positive slope, negative slope, positive goes both up or negative goes both down. That's just one way that helps me remember which one's which. And you can find your own ways to remember, or you can use mine if you want to. So let's practice a little bit of end behavior. I'm giving you a few examples here, and I just want you to find the degree, the leading coefficient, and then tell me what the end behavior is. I'm not asking you yet to figure out what's going on the inside of the graph or the middles of the graph. I just want you to know what's going on at the end or extremities of the graph. So the degree of the first function, f of x equals 2x plus 5, the degree is 1, and my leading coefficient is 2. Now, a degree of 1 tells me that's an odd degree. The leading coefficient of 2 tells me it's a positive. So I need to remember from the chart, what does an odd degree look like? Well, odd, that's in two different directions, either up and down or down and up. But positive means I'm kind of looking like a positive slope here. So that means I'm going to go down to the left, yet up to the right. Or you can just memorize the chart and go back and look at the chart. Odd and positive, if you want to flip up here, odd and positive is down, up. Down to the left, up to the right. On the next problem, f of x equals negative 1/4 x to the fourth plus x squared minus x, we have a degree, or the highest exponent, of 4. Notice that that 4 is even. My leading coefficient is the number in front, negative 1/4, which is negative. So I need an even degree. Even means they're either both going to be pointing up or both going to be pointing down. But because it's a negative leading coefficient, I'm down to the left and down to the right. Again, I don't know what's going on here in the middle. You don't have to write anything in the middle. Just put little arrows on the chart and that's going to be good enough. Next, we have f of x equals x minus 5 times the quantity x minus plus 1 squared times x minus 3. We have a polynomial, although it's not distributed out. So I'm going to have a hard time finding the degree and the leading coefficient if I don't have it distributed out. So what I'm going to do is I'm going to distribute out only the first term. I know this has lots of other terms, but the only thing I care about is the degree and the leading coefficient. I don't really care about the second term, the third term, the fourth term. I just need the highest exponent and then the coefficient of that highest exponent, which will just be the first term. So I'm going to take all of the first terms and multiply them together. This will get me x times, be careful here, x plus 1 squared. Again, I'm only taking the first term because I really don't want you spending your entire homework event trying to multiply this out and then multiply it again by x plus 1 and then multiply it again by x minus 3. This is not what I don't want you doing all this. This is going to take too much time and effort and then you're never going to get through your homework. So I just want you multiplying out the first terms. So x times x, but this is x plus 1 quantity squared, which means us coming up twice. So that's going to be x squared times another x plus dot dot dot. I know there's a bunch more other stuff over here. It's just that I don't care about what it is. So my first term is x to the fourth plus a whole bunch of other stuff. Once I know that, I can tell you that the degree is 4 and that the leading coefficient is the number in front, in this case 1. 4 is even, 1 is positive, which gives me an even degree, meaning they're both going in the same direction, with a positive leading coefficient, meaning they're both going to be going up or positive. So my end behavior will be up and up. The last one is very similar to the third example that we did here, although we have a negative 3 here in front, which means that is one of the first terms that we have to multiply through. So I'm going to multiply negative 3 times x, again times x squared, times x again, and then there will be a whole lot of other terms that I really just don't care so much about. So I'm going to put plus dot 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 over here. The function turns out to be negative 3x to the fourth plus dot dot dot. Notice I included the coefficient because it was part of the first term. This gives me again a degree of 4. Now it gives me a leading coefficient, which is the number in front of the term with the highest degree, which is negative 3. 4 is even, which means they're both going in the same direction. Negative 3 is negative. So an even degree polynomial with a negative leading coefficient. Even tells me they both go in the same direction. The negative tells me that they're both going down. So this is the end behavior for these 4 examples. We don't know what's going on in the middle of each of these graphs, and we'll have to find that out next using zeros, which is going to be on the next video.